Anyway, I wanted to start off just by saying something about Freeman Dyson. I last visited here in 2019, and Freeman Dyson very sadly died in 2020. And Dyson was the director here for many years. He was a very creative and clever scientist. And I just wanted to briefly tell one story before I get started. I came here the first time in 1985. I was 26 years old. I was finishing my first postdoc at UC Santa Barbara with Jim Hartle and Gary Horowitz, and I was hunting for another postdoc job. So I went around to various places in the US, and one of the places I came was here. And I showed up at the front door of the building out there, the one with the big tower, at probably it was around 4 o'clock on the afternoon, maybe December 15th, middle of December. It was snowing, I remember that. I was dragging my suitcase. I'd been living in Santa Barbara, so I wasn't really quite accustomed, ready for this weather. And I come in through the front door, and the person there says, yeah, what can I do for you? And I said, well, I'm here to give a talk in a couple of days. My name's Bruce Allen. Malcolm Perry invited me. And the lady says, well, I'm afraid Malcolm's away, and I don't have any record here of your giving a talk. But why don't you go down? It's tea time. Why don't you go and have some tea, and I'll see what we can sort out. And so I went down. There's a fireplace if you go in that building there. And I went down, and there was people having tea and cookies. And so I had a glass of tea and a cookie. And I was standing there looking kind of uncomfortable when this funny little guy with big ears comes walking over. And he says, oh, you look unfamiliar. What's your name? What are you doing? So we had a bit of a chat. And then I told him, he said, you know, how long are you here for? And I said, well, I'm here for a few days. Malcolm Perry invited me, but it seems like he forgot to arrange an office for me. And the funny little guy with big ears says, oh, well, I'll tell you what, he says, I'm going off to Washington for a few days, so you can use my office. And that was Freeman Dyson, the director of the Institute at the time. And so I sat in his office. His secretary brought me cookies and tea, and I was very happy. Anyway, if you haven't read it, everyone here should read this paper by Dyson called Gravitational Machines, published in a volume called Interstellar Communications in 1963. This is the first place where, for example, that constant c over g to the fifth, this power, ergs per second, appears. And Dyson does something very, very interesting. He says, suppose a civilization wants to extract a lot of energy from stars. Well, you can build a Dyson sphere and you can extract the sort of radiation, but that takes 1 billion years if you want to get 1% of the solar mass. It's slow. And he said, well, suppose you can extract gravitational binding energy from stars. Then, for example, you take 2 stars the mass of our sun, Schwarzschild radius 1 kilometer, actual radius 1 million kilometers. You bring them 1 million kilometers apart. Now you can extract 10 to the minus 6 of a solar mass by doing that. And they said, suppose you want more energy than that. Well, then you use white dwarf stars, because those are only thousands of kilometers in size. And now you can bring them much closer and get 10 to the minus 3 of a solar mass. Or he says, suppose you want even more energy than that. There's these conjectured things called neutron stars. They have a radius of just a few kilometers. And so you can bring them really close and get 10% of a solar mass of energy and binding energy out of that system. But you've got these 2 stars orbiting, and at some point there's this other conjectured thing called gravitational radiation, which will limit the process. You can't bring the orbiting stars too close, or they'll start emitting gravitational radiation and they'll merge. And he does the calculation here of what the merger time is, what the power radiated is, and so on. So it's a beautiful 5-page paper, and I recommend that I think it's now available on the internet. If not, send me an email note and I'll send you a copy of it. Very interesting paper. Okay. So I'm going to talk about the stochastic gravitational background, and I'm particularly going to talk about pulsar timing arrays, which I'll call PTAs. I've been interested in this subject now for more than 30 years. A person I've done a lot of work with on this topic is a guy named Joe Romano, who's a professor now at University of Texas, Rio Grande Valley. And so a lot of what you hear from me is going to be stuff which Joe and I have worked out together over the years. So gravitational waves have a very broad spectrum, as you know, ranging from frequencies of, let's say, 100 hertz, so periods of milliseconds, down to wavelengths where there's one cycle in the age of the universe, so 10 to the minus 16 hertz, actually probably more like 10 to the minus 18. And for example, their effects would be felt on the microwave background radiation, for example, perturb the temperature pattern. At the high frequencies, we now have operating ground-based gravitational wave detectors. Space-based interferometers at the sort of millihertz regime are going to be launched probably about a decade from now. And then at these lower frequencies of nanohertz, the most practical way to detect gravitational waves is with pulsar timing arrays. And so that's going to be a lot of the focus in the next lectures. So what do we mean by a stochastic gravitational wave background? What we typically mean is sources that are not individually resolved. So for example, if you look at the data from LIGO, you can see nearby chirps from binary systems. But then there's more distant binary systems that we don't individually resolve. And those add up to create some kind of background radiation and gravitational waves. Now eventually, detectors will get sensitive enough and it will detect those individually, and then they won't be part of the background anymore. So this background might be an astrophysical background, by which we mean, for example, compact binary coalescence sources, continuous wave sources, whoops. For example, supernova, for example. These things, the ones that aren't individually resolved, will create some kind of a background of gravitational waves. Then there's the sources that are the more cosmological ones. And what I typically think of here, and this is what got me interested in the topic, is processes that happen in the early universe. So this might be things like networks of cosmic strings. Let's say just the effects of phase transitions. So for example, the formation of bubbles of one, let's say, more stable phase of matter expanding inside the less stable phase of matter. These bubbles collide. That produces gravitational waves. And very often, these processes are modeled as a Gaussian process. Because of the central limit theorem. And I'll talk about that. And one of the things I'm going to show you in my lectures is how to actually not use those models, but to use discrete source models, which are kind of interesting, and lead to the Gaussian models in certain approximations. By the way, I'd be very happy to be interrupted. So if people have questions, please ask them. This is, you know, there's two different ways to approach a topic. You can fly over it at 10 kilometers high and sort of see a lot of landscape. I'm not going to do that in this lecture. Instead, I'm going to sort of stop at a few interesting places which you should know about and explore those in detail. But my lectures, I've got plenty of material for the 4 lectures. What I actually talk about is going to depend, for example, on what Barak decides to lecture about. So I'll probably modify what I'm doing. Okay. And by the way, the promise of gravitational waves, the reason why I got interested in them in the first place, it goes back to inflationary models of the universe. I was a PhD student when inflation was invented, and I worked on that. And when I was a postdoc, I still was working on inflation. This would have been the early, mid-1980s. And in those days, every issue of Physical Review D was like this thick, and it had 20 different inflationary models. And the next month, there'd be 20 more inflationary models and so on. And I got very discouraged about this. I thought, well, how in the world can we tell which of these is right, if any of them are? And that's the promise of gravitational waves, because gravitational waves are very weakly coupled, and so they propagate through the universe. So for example, electromagnetically, we can't see earlier than the surface of last scattering, which is a redshift of maybe 1300. Because before that, the universe is full of charged matter, and that scatters photons, and so you really can't see. But gravitational waves couple so weakly that they give you a way of looking at the universe at earlier times. Not so interesting for the astrophysical sources here, but really of a lot of interest for the cosmological ones. And so I'm going to start off by spending a little bit of time just explaining that connection. Specifically, if we have a gravitational wave detector like LIGO or LISA or pulsar timing arrays, at what time in the history of the universe do we get information? I also want to just talk a little bit about the spectrum. So let me do that first here. Yeah, this board is going to be a challenge. Okay. So something which is used a lot in the literature is a dimensionless function called omega. Some people put a GW down here to distinguish it from other possible sources of energy. And this is just to describe the distribution of the energy as a function of frequency. And the definition goes like this. You say, let's pick a volume. Now, I would say pick the volume of this lecture hall, but this lecture hall is too small. Your volume has to be at least big enough to enclose a few wavelengths. So for example, for LIGO, your lecture hall better be 10,000 kilometers on a size. For PTAs, your lecture hall better be 10 or 20 light years on a side. But anyway, pick some volume and look at the amount, the energy density of gravitational waves in the frequency range between F and F plus dF. So pick some little range of frequency, ask yourself, what's the total energy of gravitational waves in this volume? Divide that by the volume, and then that's d rho. So that's the energy density. And now, the way that you make this dimensionless spectral function is you take that quantity. So you take the energy density in gravitational waves, you divide that by the frequency interval that it was computed in, and then you normalize it by multiplying it by f, the frequency, and dividing it by the critical energy density needed to close the universe. So the critical energy density is just defined by this. If you have a spatially flat universe, the square of the Hubble constant is 8 pi g rho critical over 3c squared. And so rho critical here can just be rewritten in terms of the present day Hubble constant. And if the gods of calculation are on my side today, I guess that would be 8 pi g divided by 3c squared, Hubble constant today squared, times d rho gravitational wave, d log f. By the way, I'm very good at recognizing other people's algebra mistakes when I'm sitting where you're sitting, but I find it very hard when I'm standing where I'm standing. So I will make algebra mistakes. Please point them out to me. Okay. So this function It's just a way of telling you how much energy density is there at a particular frequency. And let me show you a plot just for fun. So of course we could do this for any source of energy density. In this case, I took the energy density in gravitational waves. But for example, we could take the energy density in the electromagnetic background radiation, the 2.7 Kelvin background radiation, and plot that. And here's what that plot would look like. So this curve here, the upper one, is a 2.7 K thermal spectrum. I've converted into omega by that formula. I got to be careful not to fall down the stairs here. So on the vertical axis, you can see log base 10 of omega. There's 1 at the top. There's 10 to the minus 5 there, 10 to the minus 10. And here's this whole range of frequency that I showed you before. So cosmological frequencies, 10 to the minus 18 hertz, 1 cycle in the age of the universe. Here's 10 gigahertz, X-band, 3 centimeter radiation. The peak of the microwave background radiation is about 150 gigahertz. So 10 to the 11 hertz, roughly. So that's where this peak is. The fact that this gets up to 10 to the minus 5, that's because the energy density in the microwave background is about 10 to the minus 5 of what would be needed to close the universe. And so, the way to read a plot like this is, provided that this peak, wherever it is, has a width which goes from some frequency f up to 2.7 times f, so that d log f is of order 1, then that's the amount of energy, that's the fraction of closure density associated with it. And I think you'll see some plots like this sort of later in the lectures, and so that's to give you some normalization. Now, just for fun, I stuck a 0.9 Kelvin thermal spectrum there. That is the temperature. So in a standard sort of, let's say, simple model of particle physics with a certain, I think, 106 degrees of freedom and so on, that's the temperature that the gravitational wave background would have if it was in thermal equilibrium with the other stuff in the universe. It would have decoupled at a certain time. Now, that thermal spectrum is almost certainly wrong. And the reason why is because gravity is so weak. So it was shown by Sakharov, Zeldovich, I think other people worked on this also, Weinberg, that the trouble is that the universe is too quick. So it expands so rapidly that the gravitational field never has a chance to come into thermal equilibrium. Very different than the microwave background radiation. The microwave background radiation, there was a period when the photon and charged particle bath was strongly coupled, and that thermalized the radiation. But that probably never happened for the gravitational wave background. So the information in that spectrum tells us something. And let me try and show you that connection. That's the next topic. Any questions about any of this so far? Yeah.
So if the coupling is so weak so that the gravitational waves don't have a time to
thermalize. Yeah.
Is it obvious that there is a source such that it can be in equilibrium in terms of energy?
I think that in all of the systems that we study, there's no equilibrium. There's a pair of stars orbiting and emitting. There's no equilibrium there. So I think the answer is no. I think the coupling is so weak. If you look at the time it would take to come to equilibrium, it's far greater than the age of the universe.
So the energy could be zero also?
Absolutely. Oh, absolutely. It could be that there's basically no background of energy in gravitational waves. That's certainly a possibility, at least apart from the astrophysical sources there, right? Those got to be present. In fact, there's models. So I don't understand Paul Steinhardt's, for example, not inflationary models, but for example, they predict zero background of gravitational waves, for example. Okay. Are there other questions? Okay. All right. So I want to now talk about the following question. So what times, this is in the history of the universe, do we get information about from gravitational waves? And here there's a very nice argument. I'm going to just use the simplest of cosmological models. So this is a spatially flat Freeman, Robertson, Walker model. T here is co-moving time. So this is the time that would be seen or measured by an observer on their wristwatch who's falling along the same paths followed by the matter. So people would say, for example, in a dust-dominated universe, this is an observer who's sitting on or riding along the galaxies. That's the time that they measure. And the Hubble expansion rate here is a dot over a, units of 1 over time. Same thing I've got appearing over here. And let's look at how the wavelength of a gravitational wave changes as the universe evolves. So the idea is, well, let's construct a simple cosmological model first. I think I'll do it over here. I'm just going to sketch this out for you, literally. So here's time on the horizontal axis. I'm going to put the beginning of the universe here. And I'm going to assume the universe went through a few phases. It started expanding, let's say, like a radiation-dominated model. So that means that the scale, sorry, this is the scale factor here, A of t on the vertical axis. So during this period, and let's say this lasted up to, say, 10 to the minus 30 seconds after the Big Bang. So here, A is proportional to t to the 1/2. Then let's say there was a period of inflation. So there's some exponential growth here. The blackboard doesn't go up far enough for me to really do it justice. So you'll just have to imagine that there's something like 60 or 70 e-foldings here, a lot of growth, but I'm going to be sloppy about it. So here, oh gosh, I'm making a mess of this. All right. That's 10 to the minus 36 seconds here. This is going to be, let's say, yeah, sorry. Good suggestion. Let me make better use of this space. Better? All right. But I don't know yet. All right, so here's scale factor A. Here's t. We're gonna have our universe have 4 stages of evolution. So the scale factor is going to go like t to the 1/2. From 0 up to, let's say, 10 to the minus 36. I think I'm just going to write 36 here. So this is log base 10 of t. Then we're going to have some period of exponential expansion called inflation. That's going to go up to, say, 10 to the minus 32. And so there the scale factor is growing exponentially. By the way, if you want to fit this model, you don't have to just match A here. You also have to match the slope. Why do you have to match the slope? What goes wrong if you don't? Suppose I build a cosmological model and I don't have my slopes matching at this point, just the value of A. Yeah? Exactly. You can actually read it off the equation that I wrote over here, right? Because the energy density, this is a formula here for A dot over A squared. And so if A dot is discontinuous and A is continuous, then the energy density suddenly jumps, which physically it can't do. So So when I write e to the ht here, you have to imagine that you've put a constant in front and also maybe shifted the time coordinate so that both a and its derivative are smooth. Then let's have another period here of radiation domination, so growing like t to the 1/2. And then finally, the universe switches. Let's see. This should be about 10 to the 5 years into the history of the universe. So I don't know, let's say 10 to the 12 seconds. And then finally, the universe is matter dominated after that. So, and here we are, 10 to the 17 seconds after the beginning. Here's t to the 2/3. So imagine that you build a cosmological model like this. So you write down a of t. You have those different dependencies. You'll have to shift these t values here in order to get both a and its derivative to be continuous. But imagine you've done that. And now you can compute h in that way. And let's figure out how wavelengths change. So the most important thing here, if we want to understand sort of cosmological effects of gravitational waves, is what's the cosmological length scale? And the cosmological length scale, I'm just going to call it L of t. This is just the inverse of this Hubble expansion rate times the speed of light. Now, what's more, if you look at this, you can see that for almost all of this model here, the expansion, I mean, this is, let's say, 44 orders of magnitude here. The expansion is dominated by that radiation-dominated era. And you'll notice that in that radiation-dominated era, this length scale, a dot is 1/2 t to the minus 1/2. And so that means that h in the radiation-dominated era, h is 1/2t. In the matter-dominated area, it's 2/3t. And so this length scale is just growing linearly with time. That's approximately 2t. So if we made a plot, and I'm going to do a bad job of it, but I've got a better one here on the slide, then this cosmological length scale, to good approximation in this, is effectively just linear. There's some little changes. It changes from 2t to 3/2 t kind of smoothly, but this is a good approximation. Now, suppose that our gravitational wave detector, let me start with LIGO, sees a gravitational wave today. So LIGO is sensitive at frequencies of around 100 hertz. Since light goes 300,000 kilometers a second, that's a wavelength of 3,000 kilometers. Now today, the Hubble scale, so if this is today here, this length scale is around 10 to the 28 centimeters. Take the age of the universe, multiply it by the speed of light. And what LIGO might detect, let's say, is a wavelength down here. What did we say? We said 3,000 kilometers. So that's about 10 to the 8 centimeters. Now let's trace backwards in the history of time. So let's look at this thing that LIGO detected and say, suppose that that's cosmological in origin. Suppose it comes from some process that happened in the universe. Well, the wavelength in this kind of Frieden-Robertson-Walker model just scales with a of t. So the wavelength lambda at any time t is the wavelength at the time the radiation was emitted times A of t divided by A at the time it was emitted. So if you look over here, you see that that's growing like t to the 1/2. It's not growing linearly with t, like the Hubble length. It's growing more slowly. So that means if you trace back in the history of the universe, this wave that arrives at our detector today with a wavelength of 3,000 kilometers, at some point in the past, that was comparable to the Hubble length. And so if those waves were produced by some cosmological process, for example, perturbations that are now within the Hubble sphere and therefore can collapse to form primordial black holes, or phase transitions which are nucleated when a scalar field, for example, aligns in a certain direction, which it can only do once it's inside the Hubble radius, those processes will form structures on the length scale of L. And so if you look at where these plots intersect, that tells you where this happened. And let me just do the calculation. I apologize for the small font here. But hopefully the idea is clear enough that you can actually reproduce this yourself on a sheet of paper. So for example, let's just write down what the wavelength is. So this is in terms of emitted wavelength. Let's write down the same formula in terms of observed wavelength. So we've got an observed wavelength today, and as we go into the past, that's a t observed. That gets, so I've got that the wrong way around, don't I? That gets smaller by the ratio of A of t divided by A of t. Let's just see that's going in the right direction. That's right. As I go to the past here, this A of t in the numerator gets smaller. So there's a formula describing this curve. And let's just set L at the time of emission equal to lambda at the time of emission to see where these curves intersect, just to get some order of magnitude idea. And so what we've got then is we've got, I see I've made a mistake here. I dropped a factor of c here. That should be 2ct. I'm going to do the same thing I'm afraid that Matthias was doing, which is I'm going to be sloppy with my c's. So if we set 2c times the time of emission, that's this curve, equal to, this should be an, okay. This equation is wrong. That should be A of t0, I believe. Somebody should have corrected me on that. Did anybody notice that? Say again?
It's hard to see what's written on the board. So we missed the different note.
I was going to suggest that people can. I was going to suggest one solution for this is you move forward. Because unfortunately, the blackboard space here is kind of limited. So if you've got really good eyes, sit in the back row. But if you actually want to see what I'm doing, you might consider moving forward. Anyway, I should check my notes, but I believe that this is correct. So if we set this, this is the ratio of T over TO to the 1/2 times lambda 0. And so we can just solve that equation to find out at what time of emission, TE, does that intersection take place. Now, let me see if I can fight with the blackboard and get this up. I was told that this is a challenge. OK. So let's just solve that. We've got 2c TE to the 1/2 on the left. we've got a t0 to the minus 1/2 times the wavelength today. So that means that the time of emission, it's 1 over 4c squared. There's a t0 down here. And let's put a lambda 0 squared upstairs. And you'll recognize here that, 2c t0, that's just the Hubble radius today. So let's just put some numbers in here to see what this works out to for LIGO. So for example, for LIGO, lambda, let's say, is 3 times 10 to the 8 centimeters. And so what have we got here? We've got, I'm going to drop the factors of 4, but we've got, let's say, 10 to the 17 centimeters squared in the numerator. In the denominator here, we've got c squared, let's say that's 10 to the 21 centimeters squared per second squared. And finally, the age of the universe, let's say it's 10 to the 17 seconds. So you cancel out the factors. And what do we get? We get about 10 to the minus 21 seconds. Now, I think when I did this a little bit more carefully, including the factors of 4 and so on, I got about 10 to the minus 22. So there's the plot, done a little bit more carefully. So here's what LIGO observes today, wavelength of a few thousand kilometers, traced back in time, and that intersects the Hubble length at 10 to the minus 22 seconds. So if we can learn something about cosmology from observing LIGO, a stochastic background with LIGO, it's going to carry information about that time in the history of the universe, which is really very early history of the universe. So that's one of the reasons why myself and many other people find the gravitational wave stochastic background so interesting. It's very weakly coupled. That means it can carry information from early times, and they really are potentially very early times. Are there questions about this calculation? There's a question? Yeah, please, go ahead.
Well, it seems like it's linear, and then it has like some slope. Like it has like some slope at the end, or is it just?
Yeah, so this is when the universe is matter dominated.
Oh, okay.
And then the slope here is the scale factor t to the 2/3. That's the last phase there. Okay? But then for most of it here, it's t to the 1/2. So when I did my intersection calculation, I just pretended it was t to the 1/2 all the way. Okay? It does make a little bit of difference on where you land, but I wanted to get the idea across. And in fact, a nice exercise, if you want to do a problem, put in a realistic cold dark matter cosmology model, which has radiation and matter and a cosmological constant, and do this calculation correctly. It's not going to change the order of magnitude of the answer. Okay, are there other questions? Yeah, go ahead.
Is there a reason I would expect all of this to come from the point where it was admitted at the scale of the Hubble length?
No, no.
I could also get like half.
Oh, absolutely. So this is order of magnitude. Okay, I want you to understand the order of magnitude here. And for example, suppose that the universe undergoes a phase transition, and it does that at a certain time, and there's a certain Hubble length. So what you'd expect is regions, for example, of one phase to form that are comparable in size to the Hubble scale, and these things, for example, like bubbles of, let's say, new phase and old phase, they might start expanding, and then they'd collide at some point. Now, when they collide, yeah, maybe they're not Hubble size. Maybe they're 1/100th of Hubble size, or 1/1000th. Okay, that's the idea. I'm not saying that this is the length scale. I'm saying it's related to that. Yeah. Go ahead.
I'm not understanding why the relevant computation is that you have to compare the Hubble scale to the see the surface of last scattering. So I would have expected that maybe you would compute when a particle is moving at the speed of light or close to the speed of light because of temperature, and then maybe the motion is so violent that you have sources and absorption of gravitational waves.
So my thinking here is very much based on having looked at things like cosmic string models, how cosmic strings form, for example. And they form when regions become sort of causally connected. And that happens at this scale. Okay? But I'm sure you can cook up lots of models where this doesn't apply. And just to show you now, obviously, what you can see from here is that this time goes like the square of the wavelength. So a lower frequency detector, that tells us about longer wavelengths, and it shifts this up. So for example, suppose that Lisa was able to see some sort of cosmological process. That would tell you about a time here which was maybe around 10 to the minus 14 seconds. So that's LIGO. 10 to the minus 14 seconds is the sort of thing you'd see with Lisa. And pulsar timing arrays, if they're seeing cosmological processes, now the wavelength gets substantially longer. This is a wavelength of 10 years. And so this intersection is somewhere around 1 second. So anyway, this is PTA. Oh, thank you. So this is one of the reasons why the stochastic gravitational wave background is of interest to me and to many other people, is just related to this promise. Okay. Fine. Good. I'm going to pop on to the next slide here, just because I've forgotten what it is. Okay. I'll come back to that.
Perhaps a question.
Yeah.
I'm just a little bit confused when you mention phase.
Like in phase transition,
Yeah, like phase transition, you refer like spontaneously integrating?
for example. So for example, you have a scalar field, let's say, that's trapped in some potential curve. It's not at the minimum. And then as the universe expands and cools, at some point it slides over and falls down. And when it does that, the region where the scalar field makes its transition becomes a bubble, where you have the lower energy density phase in the inside, the higher energy density phase outside, and the difference goes into the bubble wall. And so the bubble grows, it starts approaching rapidly the speed of light. And then there's presumably other bubbles, and eventually these meet, and the collisions between the walls create large time-varying quadrupole moments and emit gravitational waves. So that's the sort of picture. Yeah. Okay. All right. So now I want to change gears, and I want to start now doing a bit of a more mathematical description of gravitational waves and how we're going to talk about them. And this is in some ways generalizing, going into some details in what Matthias was talking about. So as he has done, I'm going to assume that there's a metric, which is the Minkowski metric, plus some perturbations. And I'm going to write out these perturbations in the following way. Now, I want to count gauge conditions. So in principle, these metric perturbations, they're a symmetric matrix. So there's 4 values along the diagonal. There's 6 values above, and then the 6 values below are determined. So there's 10 degrees of freedom originally here. And typically, in this kind of analysis, you fix degrees of freedom. For example, there's a traceless condition. That's one constraint. Then you have a transversality condition. Transversality condition might read something like the derivative of HAB, the divergence is 0. And finally, let me just call this transverse. That would be 4 conditions, but you're actually going to see it's going to be 3. And finally, there's another condition which is called the synchronous condition. And this is the condition that there's no time components. And for me, it's easiest to think about this if I let j go from 0 to 3. So I think of that as 4 conditions. And then because of that, this transverse condition becomes 3 conditions, not 4. And so now when you count this, we've put 8 constraints, and that's left us with 2 physical degrees of freedom. And so whenever somebody tells you that this is transverse traceless gauge, you should say no. It's transverse traceless synchronous gauge. You've dropped the time components. You've set them to 0. That's the remaining conditions. And what that means is it means that the metric perturbation doesn't affect clocks. That's one way of thinking about it. So with these conditions, we can write gravitational waves the following way. So I'm going to use this a lot, and so I'm going to spend some time discussing this. It's going to be a sum over polarizations. It's going to be an integral over frequencies. And for reasons that I discussed, this is going to go from minus infinity to infinity, not from 0 to infinity. Then there's going to be an amplitude, h. Oh, pardon me. Then there's also going to be an integral. I'm going to write a d omega, which is an integral over directions on the sphere. Then there's going to be an amplitude, which depends upon the polarization, the frequency, and the direction. This is a complex amplitude. There's going to be an e to the 2 pi I f t minus omega hat dot x. I'm going to explain omega hat in a second. And finally, there's going to be a polarization tensor, EA. Whoops, I better put the A upstairs here. EA, subscript AB of the direction omega hat. So we've got a sum over polarizations, an integral over frequencies, an integral over a 2 spheres worth of directions, a complex amplitude that depends upon polarization, frequency, and gravitational wave direction. There's a complex phase here, e to the 2 pi IF, t minus omega dot x. And I guess that should be ct times omega dot x. But I think I'm going to set c equals 1, just to try and reduce confusion here. And then finally, there's a polarization tensor here, which depends upon which polarization state we have and on the direction omega. And so maybe I should say here under the summation that A is equal to plus and cross. And I'm going to talk about this expansion now for some time, because we're going to be using this in the next lectures. So in terms of notation here, So let me try and be very specific about what I mean about notation. So first of all, d omega is a measure on 2 spheres. So this is sine theta, d theta, d phi. I'll draw a little 2 sphere here, and I'll draw just a little patch here. That's d omega. You integrate that, you get 4 pi. Omega hat. So omega is used in a couple different ways in this expression if you look at it. There's the integral d omega. I just told you what that means. There's HA, which depends upon f and omega. Now, what I mean by that omega is I mean either theta and phi, the coordinates on the sphere, or equivalently a unit vector pointing to that point. So that's cos phi sine theta x hat plus sine phi sine theta y hat plus cos theta z hat. So that's what I mean by omega hat. And lastly, what about these polarization tensors? So Matthias wrote those down for a gravitational wave traveling in the z direction. I'm going to write it down more generally, and this is actually kind of a useful thing to have in your back pocket. So let me just explain how this goes. So what we need for the gravitational wave propagating in that direction is we need a pair of vectors that are perpendicular to it, because that's what transverse polarization means. We can construct them by inspection. I'm going to call the first of these m hat. And I have to write down something that's perpendicular to this. But that's actually very easy to do. Oh, it should also be unit length. I just write down sine phi x hat minus cosine phi y hat. That's clearly unit length, since sine squared plus cosine squared is 1. And it's also clearly perpendicular to this, because if I take the dot product here, I get a sine phi cosine phi. And here the dot product gives me minus that. I can also write down another vector very easily that's perpendicular to both. How do I do that? Well, I take the same phi dependence as I've got up above. But I swap cosine theta and sine theta. So let's check. First of all, it's obvious that m hat is perpendicular to n hat. I take the dot product here, I get a sine phi cos phi. It cancels the cos phi sine phi. All good there. Is it unit length? Well, that's also obvious, because if I square these first two components, the cos squared and the sine squared add up to 1. I get a cos squared phi plus cos squared theta. Square of that is sine squared. That's also clearly true. The last thing we have to check is that these two are orthogonal. But that's also obvious by inspection. Because if I dot the x and y parts together, right, I get a cos squared phi here and a sine squared phi there. That adds up to 1. And so you just get a cos theta sine theta from the x and y components. But then you get a minus cos theta sine theta from the z components. So I've just written down 3 vectors which are mutually orthogonal. And by the way, I can never remember if they're right-handed or left-handed. If I got the handedness wrong, put a minus sign in one of the last two, and that will fix it. So from these, we can now write down the 2 polarization vectors. So look at this integral that I've written down here. It contains polarization vectors E plus and E cross. And these depend upon the direction that the wave is traveling in, which is omega hat. Now you notice that these m and n here also depend upon the direction of the wave. So if I write this out very explicitly, the plus polarization one is m hat of omega minus n hat of omega, n hat of omega. And I better put indices here. So A, B, A, B. And E cross it's m hat A, n hat B, minus n hat A, m hat B. So let's check a few things. For example, are these traceless? Well, if I take the trace of this on A and B, what do I get? I get m hat dotted into m hat, but that's a unit length vector, minus n hat dot n hat, which is also unit length. So I get 0. What about down here? If I take the trace of this, I get m hat dotted into n hat. But by construction, they're orthogonal to each other. So that's 0. Same for the second term.
Sorry, Bruce.
Yeah.
Like if I forget everything, you just have x, y, and z, shouldn't it be the cross one be with a plus?
Yes. Thank you very much. If that had been with a minus, these would have been transverse because they're constructed entirely out of M&M, and they would have been traceless, but they would not have been symmetric. So if I swapped A and B here, and I swapped A and B there, and I had a minus sign, I wouldn't get back the same thing. So thank you. Good. So let's just quickly check that this solves the wave equation, for example. By the way, you've got to have a decent understanding of it. If there's questions, if somebody wants to ask me a question about this, now is a very good time to do that. If there's some uncertainty here. Maybe the one thing you could still be confused about is why is the integral over all frequencies f? So for example, here, there's an important thing I forgot to say. Maybe I'll just add it at the bottom here, is that this quantity is real. So if this integral is to be real, it has to equal its complex conjugate. When you complex conjugate this, you change the sign of that argument. And so that means that in order to be real, it must be the case that HA of f and omega is complex conjugate of h of minus f and omega. That guarantees that the imaginary parts cancel in the integral. Okay. So anyway, let's check a few things about this. For example, the wave equation. Box HAB equals 0. So this tells us that if we take two time derivatives plus the gradient of h, we should get 0. So this is obvious. Look at this expression. The only place that time appears is here. And the only place that space appears is there. So if we take two derivatives with respect to time, we're going to bring down two factors of e to the 2 pi if. So imagine taking two time derivatives of this expression. Into here, you insert a minus 4 pi squared, f squared. Yeah?
Should there be a half of that integral because otherwise you get 2 times the root?
So this is just a question of how you choose to normalize your h. I'm going to use this expression. And what I meant to say here is just that in order for this result to be real, h has to satisfy that. But it's just a question of normalization. I'm going to stick with this normalization because it's easy for me to remember. OK. So anyway, imagine taking two time derivatives of this expression. You pull down a 4 pi I squared inside. And now imagine taking the gradient with respect to x twice. So the first time you take the gradient, you pull down an omega hat times 2 pi I f. The second time, you pull down another omega hat, which gets dotted to that. But of course, omega hat is a unit length vector. So omega hat dot omega hat is 1. And so what happens is you end up getting 2 pi if omega hat dot omega hat. And I guess, yeah, I think that looks right. And they cancel. So you can see from this expression, by inspection, it satisfies the wave equation. You can see that it's traceless. We already talked about that, tracing these polarization tensors. You can see that it's transverse, because if you take a gradient with respect to x of this expression, you bring down an omega hat, which dots into one of these. But these tensors are both perpendicular to omega, so the dot product gives you 0. It's symmetric. So that is one way to write down sort of the general solution for gravitational waves. And this is effectively nothing other than taking the solution propagating in the z direction but making it a bit more general. And you can think about this, you know, what's this function telling you? This function is telling you the amplitude at frequency f of the waves traveling in direction omega. And by the way, the fact that the wave is traveling in direction omega should also be obvious from this expression, because if you increase t a little bit, sort of go in the future, and you want the phase to be constant, which is meaning that you're staying on a wave front, then you have to also make x increase in the same direction as omega. So the fact that this is propagating in direction omega also follows from that expression. Okay. So anyway, so you can think about this function HA of f and omega as telling you something about the amplitude at frequency f in direction omega. All right. I've got to watch the time, or I'll run out. 12:32. So I've got until 45, right? Okay. All right. There's a few other things I had intended to mention here. Maybe I'll just briefly summarize them. I think I'll just mention one thing which is interesting, and then I want to start on a calculation of the effect of this on a gravitational wave detector. I may not get all the way through that, but let's see how far I get. Let me just mention a couple of interesting things about this. These are factoids, but they're very useful. If you look at my definitions of omega m and m hat and n hat, you'll notice that there's a freedom here. I picked m hat and n hat to be particular vectors perpendicular to omega, but I could rotate those, and I'd get another pair. So there is a remaining local gauge freedom here. I could introduce an arbitrary function psi, that's an angle, of theta and phi, and I could rotate m and n by that function. The function doesn't have to be continuous. It could just be anything. And I would get a perfectly valid other solution to the equations. So in fact, the way that, I forgot to show you. So these are the patterns of these two different plus and cross polarizations. You notice that the pictures are rotated by 45 degrees from one another. And you can see that rather easily. If you do a transformation where, for example, you define m hat prime, let's say, to be cosine psi m hat plus sine psi n hat, and you define n hat prime to be minus sine psi m hat plus cosine psi n hat. And here psi is just any arbitrary function of theta and phi. Doesn't matter what it is. This defines another pair of transverse vectors. And it's very interesting to see how these transform between themselves under those transformations. And what you'll find is that when you do that rotation psi by 45 degrees, this turns into that, and that turns into, I think, minus this one. And actually, there's a nice thing. It's quite convenient for some calculations, and I'll use that in later lectures, which is to define complex polarization tensors. And these actually are physically meaningful, so I'm just going to write them down. You notice that this doesn't have a plus or a cross on it. So this is a complex polarization vector. And if you want to get the other one, because we have to have two to have a basis, you just take the complex conjugate of this. And if the gods of algebra are smiling on me, you can write this in that form. Let's see if that's right. So, for example, there's an m hat here. The real part is m hat minus n hat. So that works. And the imaginary part is m hat a n hat b plus n hat a m hat b. So that also works. So if we want to, we could also write this expression for h slightly differently. We could write it in terms of these complex polarization tensors. Also rather useful. You notice now there's no sum over polarizations. Oh, but there is a real part. Pardon me. And if you look carefully at how this expression is equal to that one, this function h has a real part. Sorry, this function h is a combination of h plus and h cross. I might not get the signs right here. But roughly speaking, it's h plus f omega plus I h cross of f omega. And this function does not have the transformation property that complex conjugating it is equivalent to changing the sign of f. So it has twice as much information in it as h plus and h cross. Okay, it's also a convenient form. I think there's probably a couple of things that I had meant to talk about here, which I haven't, but I'm going to move on. Perhaps I make one last final remark, which is a nice exercise is do this rotation of the basis and ask how this complex polarization tensor transforms under that. And it's rather pretty, because under the change of basis, what happens is that EAB of omega just transforms to e to the 2i psi AIB of omega. And this is actually the definition of spin, or helicity. How does the waveform transform under a change of coordinate basis? And so this transformation law, the fact that if you transform these vectors orthogonal to the propagation direction through some angle, and this polarization tensor undergoes a phase change which rotates it twice that, that's the reason why people say gravity is a spin-2 field. It follows directly from this. Okay. All right, I have just a few minutes left. I think I want to get started on a calculation of how gravitational wave detectors respond. This is the calculation that Matthias did, but a little bit more general, because the calculation he did was for the case where the gravitational wave arms are short. And I think I've got a couple slides here, which I will use to try and illustrate that. So I'm now going to talk about gravitational wave detectors and how this formula is related to things that you observe. And I want to make one point before I go on, and that is this function, h, this is the amplitude of gravitational waves going in a certain direction at a certain frequency, up to perhaps some subtleties related to quantum mechanics. There is some function. I'm not a religious person, but if I was, I'd say that God knows what that function is. We don't, but doesn't mean it doesn't exist. So our universe does have, as long as you're away from the sources, some value for this h. And everything that we're going to be doing subsequently about things like statistical analysis and detection methods is because we're ignorant of that, because we don't know what that function is. We can construct functions which might be similar in some of their properties by building, imaginary systems containing sources at various points in space, and we can say, here's what H would be. But you should imagine to yourself in thinking about this that there really is some H. You just don't know what it is. And so, for example, when I write down some expression that's going to involve an integral and it has H in it, you should be thinking to yourself, there really is an H, and if I knew enough, if I knew what that function was, I could calculate, what that quantity is. Okay. All right, so let me just get started now on talking about gravitational wave detection. I want to start sketching out a calculation. I'll finish it in the next lecture. And let me make a drawing for you. So this is going to be a space-time drawing. And I'm particularly interested in this pulsar timing array case. So how does this work? So the idea is that here we have a bunch of pulsars. Those are rapidly spinning neutron stars. And some of them are extremely good clocks. And so you should imagine, first of all, just replacing these things with clocks. So there's clocks. And these clocks could also be lasers if you were talking about LIGO. So the idea is that as the signals, the ticks of this clock, the electromagnetic pulses travel to Earth, they pass through the perturbed space-time. It's perturbed because of gravitational waves. And this, of course, affects the clocks. Roughly speaking, if the gravitational wave, let's say, is in a positive phase here, then the light coming from this clock will be redshifted to higher frequencies. If the gravitational wave amplitude is negative, then the signal is actually going to be blue shifted. The frequency gets lowered. And so the propagation of the light along this path is sampling the gravitational wave field. And so a space-time drawing, would look something like this. Here's the pulsar. So this is space going along here, time going there. There's the pulsar at rest. Here's the Earth. I'm going to place that at the origin of coordinates. And the pulsar is emitting radio pulses which travel through space-time to the Earth. And these are effectively sampling the metric along that path. And that affects the arrival times. And there's a very nice formula that was written down in 1967 by Sachs and Wolf. Sachs and Wolf were at UC Berkeley. And the microwave background radiation had just been discovered. And they were thinking about the following thing. They thought, OK, as photons come from the surface of last scattering to us, they're passing through metric perturbations. And so those metric perturbations, they might cause these photons to arrive with higher energy or lower energy. And so they'll create temperature perturbations. And they wrote down a formula for the temperature perturbations. So the idea was you've got a photon traveling along some path. And how is the temperature of that photon, or the frequency of it, affected by the gravitational waves along that path? And they wrote down the following formula. Delta T over T, I'm going to call this Z, redshift. It's an integral along this path. And I think I should actually look at my notes and see how I coordinatize this. I guess I'll be sloppy. I'll just write it down now because I'm going to be finishing this calculation later. So the idea is that we're going to parameterize this path through space-time by a variable called S. And you take the time derivative, so that's the derivative with respect to the first argument, along this path. You multiply by half. That's called the Saxonwell formula. And this actually, I mean, it doesn't just tell you how the temperature of a microwave background photon changes, because relativity affects all clocks in the same way. It can be a laser frequency standard. It can be the period of a pulsar spinning. Doesn't matter. So this formula can be applied here just to figure out what's the effect on, for example, the frequency of that spinning pulsar as seen from the Earth. This also tells you, for example, how the laser frequency changes, for example, in LIGO, or how the phase changes, which is the calculation that you were doing earlier. So I'm going to start setting up this calculation now, and I'm going to finish it at the next lecture. So we need a space-time path here. So we've put the Earth. By the way, when I say the Earth here, I should make one other point, which is that, you know, the Earth is doing a complicated thing. It's orbiting around the sun. It's spinning around its axis. And so when, for example, a pulse from a pulsar arrives at the Earth, you know, depending upon where the Earth is in the orbit around the sun, this will advance or retard the arrival time. Similarly, depending upon how the Earth is spinning. So when I say Earth here, actually, what I really mean is the solar system barycenter. That's the center of mass of our solar system. It sits slightly, just roughly at the edge of the sun. So it's about a million kilometers from the center of the sun. Its position is known to within tens of meters. And it's most strongly affected, for example, by Jupiter, also by the position of the moon, some other things. So, sorry, what am I saying? No. Okay, it's primarily affected by Jupiter and by the nearby planets. That's the correct statement. So, okay. So let's start setting this up. So we want to integrate along a path which at s equals 0, for example, starts at the pulsar. So let's put the pulsar here. It's going to be at distance L. So let's put the pulsar at position L p hat. So L is the length, p hat's the location. And let's let x of s, let's see, I want it to be, I guess, L minus s times p hat should be right. So when s is equal to 0, down here, the position is at the pulsar. And then as s increases to L, we end up at the Earth. So that's the spatial position along this path. So here's s equals 0 at that end. Here's s equals L at that end. And let the time as a function of s. So I want to be a little bit careful here. So this, again, when s is equal to 0, this should be minus L. So it's probably s minus L. So when s is equal to 0, we're down here at t equals minus L, and then as s increases to L, we end up there. So here's a linear path through space-time that describes that. And I want to know not just the effect on this photon, or this, sorry, this isn't this radio pulse, but also on a later radio pulse. So I'm going to actually just write plus tau there. So now if I set tau equals 0, I'm describing this path. If I set tau equals 1, I'm describing the path, which is 1 second later. I think probably, if I look at the clock, I'm supposed to end at 12:45, right? This is a good time for me to stop. Let's stop here. Anybody who wants to see if they've understood what we're doing, do the following. Take that formula and take this plane wave expansion, or that one, it doesn't matter. Take the time derivative to compute h dot. Plug in x and t. And you see, you're going to take the derivative of something, and then you're going to integrate it. So you're guaranteed to be able to do the integral easily. When you take the derivative and you integrate, you're going to get two boundary terms called the Earth term and the pulsar term. So when we come back next time, I'm going to do that. And I'm also going to show how to get Matthias's formula. And then I'm going to start discussing in some more detail how pulsar timing arrays work. Thank you.